Afternoon. I would like to ask you, please, later, not now.
Okay, good afternoon. It's a pleasure to introduce the next speaker, Professor Cesar Joita, and the talk is bifurcation of fine maps and the real and complex settings.
Okay, thank you very much. Yeah. Should I stay here, right? So this is part of section F5. You have the title there. This is the first lecture. It will be the second one given by me later on today. And then two more by Renato Tuesday. So, and I will start with the first definition. This is the beginning. So as you can see there, we denote by K either the real field or the complex number field. And suppose we have a polynomial map. Polynomial map defined on K to the M to the K to the P. And we assume that M is greater than or equal to 2P. And we look at a value in K to the P, T naught. And this T naught is called, so that the function f is topologically trivial at this point T naught if locally f is nothing else than a projection map. By the way, trivial in math means simple, right? So, and the map on the right, P2, is the simple possible map. So f is simple around T naught, this point T naught, if locally this map via a diffeomorphism is nothing else than a product. Yeah. And so this is the definition of a typical point. If T naught is not typical, it's called atypical or a bifurcation point. And we denote by B of f the set of possible all possible atypical values of f. And this lecture, F5, the entire lecture is about this set, B of f. This set is not that easy to understand in general. It's not that easy to describe. In fact, it's very difficult in full generality. So it's not an easy task to describe this set, but we do our best and obtain some results about this set. Okay, and I will start with a very obvious remark. If you have a regular value and the T naught and if you have a typical value, then the map F must be a submersion around where on the pre-image of that set D that was that appeared in the definition. So it must be a submersion because the projection on the right it's a submersion. And we're going to denote by single f the set of points where f is not a submersion. That means that B of f must include, B of f anyhow is closed. If you look at the definition, B of f is a closed set. So B of f must contain the closure of f of single f. That's clear. And then you can ask a dumb question if you want. Suppose that single f is empty. There is no singular point for f. So that means f is just a submersion. Can you deduce from here that B of f is empty? That means f is just trivial all over the place. And okay, you might say, look, Of course, it's not like that. How can it be? Just from being a submersion, how can you deduce local triviality all over the place? Well, indeed, I mean, you're right. I mean, it's a kind of dumb question. However, I recall you that we have what's called Ehresmann vibration theorem that says that a proper submersion is actually locally trivial. Everybody knows what proper means. Yeah? The pullback of a compact set is compact. So if you start with a submersion defined, for example, on a compact manifold, and then it's for sure locally trivial. Obviously, polynomial maps are not proper, yeah, and are defined on R to the n or C to the n. They're not proper. But if they were proper, then we'll have a submersion, or we'll have a local triviality. Okay, and one more thing. If it happens that m is equal to p, so the dimension of the source is equal to the dimension of the target, this question, as dumb as it looks, is nothing else than the Jacobian conjecture. And even if you didn't hear about it, it's relatively famous. Yeah, I mean, you don't get a $1 million if you solve it, but still, it's going to be fine for you to, for example, in your PhD thesis to solve the Jacobian conjecture. You'll get a nice job. Anyhow, this conjecture is false in the real case. This was proved by Pinchuk, and the proof is not that easy, but is completely open for complex numbers. And because I mean, we're not going to touch the Jacobian conjecture. Don't worry. That means we're going to assume from now on that m is greater than p. So we are in this situation. We have a map from km to the kp, m greater than p, and let's say that it's a submersion all over the place. The singular set is empty. Well, the same question: is it true that F is a local trivial map? And the answer is no. And it's a very simple example, but you're going to see this example in every book, course, or whatever. This is due to Broughton. The map you have it over there is x plus x squared y. If you do the computations, you take the derivatives, you will see that this map has no singular point. At the same time, if you look at the fibers at the preimage of a point, you will see that in case k is the field of real numbers, the fiber has two connected components for t not equal to 0, and at 0, you have three connected components. Well, if you work with complex numbers, the fiber has two connected components if the point is not equal to 0, and above 0, you have two connected components. That means that F is not a locally trivial vibration around 0, even if it's a submersion. Yeah. Okay. But I mean, you know that you see an example, and you have to think a little bit about the meaning of this example. I mean, what can you learn from this example? And here we can make another remark here that if you take a large ball, which is going to intersect, if this ball intersects the fiber above T0 transversally, strengthening of the Ehresmann vibration theorem tells you that on this ball only, F is a trivial vibration. So on something large but bounded, F is trivial. Yeah. Well, what does that mean? That means that the problem must be far away. That means at infinity. Yeah. So that's one lesson that we learned from this one. And in fact, people gave a definition for triviality at infinity. You have it here. So f is called trivial at infinity. If you can find a compact set in Km such that f is not trivial all over the place, but is trivial outside this compact set. Yeah. So that means that is trivial at infinity. Okay. And then, because we looking at Broughton example, we saw that we might have problems at infinity. People try to put conditions at infinity to ensure triviality. And you'll see sufficient conditions at infinity in Renato's talk Tuesday, tomorrow. And but if you want to see plenty of them, you can check up Mihai Tiber's Cambridge University Press book from 2007. It's called Polynomials and Vanishing Cycles, and you'll see there are plenty of conditions at infinity. Here, I'm going to introduce one of them because I'm going to use it in a second. So you look at this this function, rho of x, which is the norm of x squared. Doesn't matter that you work in over complex numbers or real numbers, the function is the same. And we denote by m of f the critical locus of this map f of f and r and rho. And I mean, this set m of f is nothing else than the set of tangencies between the fibers of f and spheres. So this is maybe the fiber comes like that. So if this is a fiber, you have points of tangency here and here. So these points are in the set M. So you take all fibers, you take all spheres, and you put them, these tangency points, in the set M. If you want the equation, you just write down the equation for the matrix that gives you the critical locus of the function f and rho. But M of f is the set of tangencies. So some people even call it like that, the set of tangencies. And it was proved by, I didn't write there, by, associated to this set M of f, you can introduce the following set. So it's the set of points. So it's a set of points in Kp, T0, such that we can find a sequence of points. So you have T0 here. Here, let's say this is the M of f. You have points, but in fact, you can work with curves that go to infinity, such that, but on M of f, not anywhere else, such that the value of the function, so this is, for example, f of x1, x2, x3, and you have here f of x1, f of x2, and so on. And this sequence of points should approach your point t naught. So this is the set. I didn't give it a name, but I think anyhow it's there. And it was proved by Nemeti and Zaharia that if you have a regular value which is not in that set, then this value is typical. Yeah. So you have a sufficient condition. But here you have to be aware that this is not an if and only if condition. And in fact, there is an example of Păunescu and Zaharia that give an example of a polynomial map from C4 to C, which is a trivial fibration, and this set is not empty. You see the trivial fibration all over the place, and the set is not empty. Sorry. And I want to make a remark here. People use this word infinity. You have to be aware when you use the word infinity. It could mean several things. The easiest way to look at infinity is to compactify with 1 point, Alexandrov compactification. And this compactification is in some sense the best because it's invariant under coordinate changes of coordinates. Here, this condition that norm of xk goes to infinity, it's invariant. It means exactly this, that xk goes to the 1 point compactification of kn. Yeah? So this is the 1 point compactification condition. However, the function rho is not invariant under changes of coordinates. Yeah? And in fact, Păunescu and Zaharia example is an example when you change the coordinate on C4, changing that, you change actually the function rho, you obtain something else. At the same time, people, when they talk about points at infinity, they think maybe 1 point compactification is not good. I mean, it's not fine enough, just 1 point. They try to put something else at infinity. They try to compactify it in some different way. And because you talk about polynomial maps, the most natural way to compactify is to go to the projective space. So you consider Km or Rm or Cm in the projective space. But again, be careful over there. Once that you change the coordinates in Rm, you change the infinity. So it's not it takes a little bit of care. That's what I want to say. Good. And another trivial remark about locally trivial fibrations. If it's locally trivial, then all the fibers are the same, are diffeomorphic. Yeah, it's obvious. And then the next question if we know that the fibers must be the same, can you detect atypical values, bifurcation values, just by looking at fibers? So you look at the topology, if you want, or the different topology of the fiber, and once that you see that they're all the same, can you say that that point is a typical value? But you think about that, I think maybe it's too difficult, or maybe it's not true. But you might say, okay, maybe in general it's not that easy to decide, or it's not true. And what about some small values of K of MMP? For example, if you look at polynomials mapped from R2 to R, this is the simplest possible case. It doesn't get any simpler than that. Because in this case, the fibers are one-dimensional. You look at the regular values, that means the fibers are finite unions of circles or lines. Differ with circles S1 or differ with R. That's all. The fibers are very simple. And the question is for this kind of maps. If you have this kind of maps from R2 to R, and if you know that the fibers have the same topology around a point, is it true the map F is locally trivial? And the answer is no. And an example was given by Mihai Tiber and Sam Zaharia in Manuscripta Mathematica in 1999. I wrote the example here. I mean, you don't have to read those equations. But I mean, I put them there to impress you, yeah? But if you look in their paper, you'll see a bunch of examples. It's not the only one. There's several of them with different properties. Anyhow, in this example, if you look at 0, 0 is going to be a regular value. On an interval around 0, the fiber of F has 5 components, connected components. Each one of them is just a line, but still F is not a locally trivial fibration. And what's the problem? In general, if you look at maps with one-dimensional fibers, that means maps from Rn plus 1 to Rn, there are some bad things. I mean, I said bad things. Yeah, bad things that can happen. And I'm going to draw some pictures. So it is possible that some connected components of the fiber vanish. What does it mean? Well, say this is a fiber above, so F is equal to 1/2. It's one component of the fiber. Might be that this is the one component of F inverse of 1/3, and so on. And when T approaches 0, F inverse of T has a connected component that goes all the way to infinity. And at 0, you don't see it anymore. I'll write down the precise definition, but this is the meaning. Another bad thing that can happen might happen that a connected component, I'm going to erase here. So say this is a connected component of F inverse of 1/2. Then you have a connected component of F inverse of 1/3. And you keep going. And when you approach 0, here instead of having one connected component, you have 2. So you end up with something like that. One more phenomena. I wrote there compact component, but compact component means circle. So you have a circle here for 1/2. They have another circle, larger circle like that for 1/3. Another circle like that for 1/4. And you go to infinity, this circle becomes a line. Go ahead. Yeah, but you're right. But here we are talking about regular values. And that doesn't happen. Yeah? Yeah, you're right. If you didn't have regular values, then that will be a possibility. But for regular values, we don't have that phenomenon. Yeah? And what I wrote here, I mean, in pictures, can be actually written formally. And for vanishing, you say that we have vanishing at infinity as t goes to t naught. If you can find a sequence of points tk that goes to t naught, such that we can find a choice of a connected component in each fiber, ck, and this ck is locally finite. Locally finite means that leaves any compact set in finite time. Yeah? This is the meaning of vanishing. You don't see it in the picture. So this locally finite stuff is the vanishing phenomenon. And if there is no vanishing, we simply say that, I mean, we write NV non-vanishing at T0. And for splitting, it's a definition of a limit set of a sequence of sets in RM. Probably you have seen it before. You say that so you have a sequence of sets, and a point in RM is called the limit point. If you can find points on each of these sets that go to this point. Yeah. So I'm not looking at limits along the one set only, but I have to look at a sequence of this. So let me do. So you have a sequence of sets, and the point here is a limit point if you can find a sequence on each, or at least in on a subsequence of this set. So this is the limit set, and with this definition, we say that there is no splitting at infinity if whenever you choose a sequence of points in the target, and you have some connected components in the fibers, the limit set is connected. Yeah? So the limit set of a sequence of connected components is connected. And for the second phenomena, I mean, if you have circles that split, the circles are connected, then the limit is still connected, but something bad happens. And we say that you have strong non-splitting if this doesn't happen. I mean, if you take limits of compact sets, you get something compact in the limit. Yeah. So these are the two definitions. And with this definition, you can write some sufficient conditions for local triviality. And in fact, they are if and only if conditions. All these conditions are if and only if. That means that they're characterization. So the first one says that if you know the Euler characteristic of the fiber is constant, so not the topology, but only the Euler characteristic, and you have non-vanishing, then that implies local triviality. If the Betti numbers are constant and you have non-splitting, then again you have local triviality. Or if you have non-vanishing and strong non-splitting, then you have local triviality. Yeah. And I'm not going to give you proofs. The proofs are, you can find them in Mihai and Zaharia's paper that I mentioned before, for maps from R2 to R, and for maps from Rn plus 1 to Rn. They're in Mihai and myself paper in 2017. Okay. So this is at the theoretical level. Okay. But nowadays there is this, I don't know if it's fashion, but it's not normal to be like that. People try to do computations with computers. Yeah, it sounds, but that's true. So people try to come up with algorithms that do something. And together with Renato and Mihai, we thought about the possibility of detecting this bifurcation set we try to come up with a algorithm or a procedure that looks like an algorithm for detecting the bifurcation locus. And at least I said maybe let's start with maps from R2 to R because it's the simplest case. And we managed to do that. We are not computer scientists. I mean, we don't write code, but we understand what an algorithm is, what it should be, and what an algorithm does. Yeah. So even if we don't know how to write code. I mean, in principle, we know what that means. But I mean, we have this criteria, the previous criteria. So this theorem. I mean, they look they look simple. Yeah, all these conditions are simple. You look at moving the fiber, see what happens with connected components. They are, but this is a limit process. A computer doesn't know how to deal with this kind of stuff. Yeah. By the way, a computer is not a human being. I don't know if so. I mean, we said we should use this characterization, but in a different way. I mean, something that can be done on a computer. And the first thing that we did, so this infinity stuff. Again, infinity, if it's just one point, is too much. I mean, it has too much information inside. And then you try to enlarge the infinity to distribute the information. And we do that by compactifying R2 to P2, not to just with one point. And you know how this is done. You identify R2 with an open set in RP2. As a notation, L infinity is the line at infinity. And for a fiber, the fiber has the equation f of x and y equals t. You homogenize this equation. You take the homogenization of f, denoted by f tilde, and you set it equal to t to the power z, t times z to the d. Yeah. So this is the setting. And we want to move the splitting and vanishing conditions at infinity. And you think about, I mean, I'm raising now that phenomena with components that go to infinity like that, or that one that split at infinity, and you think that you put yourself at a point at infinity, and you think what you see sitting there. So you take your chair, you go to at infinity, sit on the chair there, and see what happens with components coming toward you. And I wrote here the formal definition, but let me draw the picture. So you have here a point at infinity, and you look at a coordinate chart around this point. Yeah. I think I wrote the coordinate chart on the top line is u. Made the choice here. Let's say the point at infinity is 0, 1, 0. Yeah. You have the coordinate chart which is isomorphic to R2. Over there, GT is the equation of the fiber written from the point of view of P. Yeah. GT equals 0. This is a CT. This is the fiber seen in this chart. And here you have this disk at this point PT naught. And the first one is the splitting. Splitting, remember, means that you have a connected component that goes, so it's like that, and goes to infinity. Yeah, when you travel like that. And over here, you are going to see an arc that starts on the circle and ends on the circle, and approaches this point. And at the end, so in fact, let me do it here. At the end, you have something like that. At infinity, this point is at infinity, so that means in R2, you don't see this point. So you have this segment split in two. Yeah. So this is the first condition. And the second condition is about vanishing. And what you see there, you see, so you, again in d epsilon, you see a loop. Once that you have something like that, this one closes at infinity, that shrinks. And at the end, you have just 1 point. This is the vanishing. Okay. And with this preparation, you actually can prove that if you have a value for f, for the initial function f, then this function is atypical, it's a bifurcation point. If and only if you can find a point at infinity p, such that we have either splitting or vanishing. That means that we have now a criteria for bifurcation, for the bifurcation point in terms just of phenomena at infinity. Good.
One question. If you you compactify to the projective space, and then you have a whole line, a smooth line at infinity, the horizon, so to say, and this horizon does not appear in your pictures yet.
Well, yes,
Does it play
here.
a role?
So here, this is the point at infinity. This point here is on the infinity, but the fiber intersects the fiber at the fiber ft intersects the line at infinity only in a finite number of points. And I choose one. I take a small disk, and then here this is just R2. Yeah. So we have here the line at infinity, but it's not touched by this. We can do it for like this here, but you don't care.
Okay, I would have expected that the component that is touching the point also has to do a tangent touch to the line at infinity.
No, because you don't assume this this component I drew like that could be singular. So you don't know that it's smooth. If you do it tangent, that means you have some smoothness there, but you don't know if it's smooth or not, and you don't care. Yeah.
Okay.
But the line at infinity is there. Good. Now, as a principle, and this is obvious, but I wrote it there just in case. So to find atypical points at infinity, first find a larger set, but a finite set. And then you have to test for each point if it has problems or not. Yeah, this is and to find, I mean, to have a nicer geometrical picture, or I'm going to bring in the picture that set M of f and the set of limits over there that I started with regularity few slides back. But to better understand geometrically, first we have a function. A function, I mean, you know what's a function. But sometimes you have to look at the function from a geometrical point of view. And then it's useful to you look at the graph of the function. Yeah. When you talk about continuity, for example, you draw graphs of functions. And here, I wrote just the graph of a function of the function f, but in this context. Yeah. So this is the definition. You look at points in P2 times R. That satisfy that that equation. This is the equation for the fiber of f written in homogeneous coordinates. And this set comes with two projections, one on the first component and one on the second component. And if you look here, the graph of the function gives you an embedding of R2 in this set. And then with this in this setting, you look at that set of tangencies, M of F, and you take the closure in X. This set, M of F closure X here, encapsulates also that set of points that you have that go to infinity and go to a point here. If you write it down, you'll see that in this set you catch those points. Yeah. So this is just another way of bringing them into the picture. And what can we show? It's not very difficult. That if you look at points P, T naught, so this point is at infinity, T naught is a point in Rk, where you have splitting or vanishing, I mean, with the definition that I gave you before, then this set of points is inside this intersection, the intersection between MF closure X with L infinity times R, and this set is a finite set. So this is the overset that I was talking about. You have a finite set sitting at infinity, and you know that all points with problem are here. I didn't say that they didn't tell you how to compute this set yet, but anyhow, this is the set, and you have to compute this set first, and for each point here, we have to decide if you have splitting or vanishing. If you do that in a algorithmic way, you have your algorithm to detect bifurcation. And in order to do that, you need some more topology. And because this, even at infinity, splitting or vanishing is about a sequence of connected components. It's a continuous phenomena. And you don't know how to test, I mean, how many fibers you can test with a computer, 5, 10, or 100, but not infinity many. And this topological theorem does the job for you in some sense. And the theorem says that map tau, sorry. So the map tau is the projection on the first component on P2. And this theorem says that this map tau is actually locally trivial on some segments that do not contain the origin, the point that you work in. So if you go a little bit to the left and a little bit to the right, the left and right, then you have something topological trivial. Okay, so this is the math preparation. I'm not going to go into the algorithmical details. It's not the time, but over here, when you write down the proof here, you'll see that you can estimate these epsilons very precisely in terms of your data. That means you can write something on a computer that does this stuff for you. With a little bit of care, you'll see that once that you have this triviality, you can decide if you have splitting or vanishing. And third, you have to compute the set M tilde in an algorithmical way. And what does that mean? I mean, if you look at the definition, it amounts to this kind of problem. You have to compute all limits, all possible limits of this type along a curve. So you have your curve that is the curve that you get when you write the equation for M of F. You go along this curve, and you have your function f, and you have to compute this limit. I said all possible limits because this curve might have several components, irreducible components. Yeah, and the way to do that to do it is to use complexification. You go to the complex field, you use Puiseux parametrization, you do some more thinking, and then you can get it in a concrete manner. Yeah, and I'll stop here.
So, some questions, remarks? Okay, we'll return in 5 minutes.
Yeah. Okay. Let's start the second part. So this is the same story about bifurcation locus of polynomial maps. However, now I'm going to look at sorry guys, at complex polynomial maps. And of course, you can ask if I talked about real polynomial maps, and Renato will do too about real polynomial maps in maybe in more general setting. Why not treat complex polynomial maps as real polynomial maps? Because if you have a complex polynomial map, say from Cm to Cp, you can treat it as a real polynomial map from R to the 2m to R to the 2p. Well, the point here is to use the complex structure to get final results. Because complex polynomial maps come with a package. It's the complex geometry package. And believe me, it's strong. I mean, when you compare it to the real world, real polynomial map, real analysis is strong. I mean, you have plenty of powerful tools. And maybe we'll talk a little bit at the exercise session about this, the difference between real and complex analysis. And so my point is to look at, and we're going to look, because only at polynomial maps from Cn plus 1 to Cn. So again, fiber dimension 1, because it's easier. Not because it's not interesting to work in general, but it's easier to work with this type of maps. But we want to look at this situation using complex geometry, if you want. And I will start with a statement. So, and then we'll see what's going to happen. So the statement is the following. Suppose you have a polynomial map from Cn plus 1 to Cn. You compactify Cn plus 1. And you get Cpn plus 1. You look at the fibers of F. And for each fiber, so you have F inverse of T. This sits in Cn plus 1. This one sits in Cpn plus 1. And I can take the closure of this one here. I obtain an algebraic variety. Not smooth. Nobody says this smooth. But it's an algebraic variety. This variety has a degree. This is a curve now. So you have a curve in Cpn plus 1. As if you have an algebraic variety, suppose that you have a pure dimension. It means all components or irreducible components have the same dimension. You have the notion of degree. Did you see this before, or yeah? Everybody, or? So degree. If you have something of dimension v, let's say in Cpn plus 1, of dimension k, m, dimension k, you look at planes of dimension m minus k. This is just planes of dimension m minus k, generic, and again this word generic, and you take the intersection. This is going to be a bunch of points, and this is the generic number of the points of intersection. This is the degree. And the theorem says that if this degree is constant around a point which is a regular value, and if the Euler characteristic of the fiber is also constant, then this point is not a bifurcation point. So, constancy of the Euler characteristic of the fiber, constancy of the degree of the compactification of the fiber gives you triviality. This is a pure complex result. You don't have something like that in a real algebraic geometry, right? And let's look at a particular case. Let's look at the case n equals 1. That means you look at maps from C2 to C. And then, when you compactify the fiber, what happens at infinity? In general, when you look at this equation, f equals t, and you homogenize, yeah, f tilde equals t to the z to the d, let's say something like that. If you add one more variable, the intersection with the infinity, you have no idea what happens with this equation at infinity. But if you're in C2, you have only points at infinity. That means that the degree of ft is nothing else than the degree of the polynomial f. So in this special case, the degree of f bar t or lambda is constant by nature. That means in this case, you don't need this extra condition. So that means the only condition is the constancy of the Euler characteristic. So as a consequence, that if the Euler characteristic is constant, then the point is not a bifurcation point. And this is what's called the Suzuki-Ha-Le theorem. Yeah. So again, this is only over the complex numbers. And then so you saw the result. For n equals 1, all that you need is the Euler characteristic. In our theorem, we said that in general, as a sufficient condition, we put there the constancy of the degree. We put an extra condition. But our theorem is just a sufficient condition, not an if and only if. And you might ask, maybe just a weak theorem. Maybe, in fact, you don't need another condition. If in the case n equals 1, you need just Euler characteristic of the fiber to be constant. Why would be in general? Need something else. Yeah. And it turns out that you have this example. The reference is there, Ha and Gen. It's a map from C3 to C2. That if you do the computations, you don't have to do them now, but if you do the computations, you'll see that the origin 0, 0 is a regular value. If you look at the fibers, the fiber above 0 is going to be C star. And for generic lambda, the should be generic, generic T here. It's not lambda, it's T. Generic T. The fiber above T is the disjoint union of two copies of C star. However, the Euler characteristic of C star is 0. 0 plus 0 is 0. That means the Euler characteristic is constant. So the Euler characteristic doesn't suffice. But Euler characteristic is just a topological invariant. It's not the only one possible, right? And you think maybe it just happens that the Euler characteristic is not strong enough. Maybe you need something better. For example, Bethe numbers. Yeah. And it turns out that Bethe numbers are not going to help either. And you have this example of a map from C3 to C2, the same dimensions. We have the equations there, but it's not, again, I wrote the equation just to impress you. Are you impressed? No, so doesn't matter. You have a regular value, and the fiber, all the fibers are just 2 copies of C. So the fibers are isomorphic. And still, 0, 0 is not typical. Still, you have a bifurcation point at origin. And what happens? I mean, why do you have this why is not a regular value? Well, when you approach 0, 0, it happens that 1 copy of C, so this is the fiber was 2 copies of C. And when you approach 0, one of these C vanishes, and the other complex line splits into 2 complex lines. Yeah? It's the same phenomena as before, as in the real case. And then with this picture in mind, you can say maybe we have the same story as in the. I didn't do anything. We have the same story as in the real case. Maybe with vanishing, we can solve. I mean, we can give a characterization because after all, we want to characterize the bifurcation locus, and maybe this is one way to do it. Okay. So I recall the definition that I gave in 1 hour ago I wrote it again because I didn't know that the 2 talks were going to be back to back. So you have the definition of vanishing. And it turns out that, so this was the theorem in the real case. In the real case, we proved that if you don't have vanishing, and if the Euler characteristic is constant in a neighborhood of T0, then you have local triviality. But by the way, I should say that this statement, if you look at this statement, but for maps from R4 to R2, this is not true. So that means if you look at polynomials maps from C2 to C, but they're not complex polynomial maps, they are real polynomial maps, yeah? The statement is not true. Yeah. But if you're in the complex setting, maps, polynomial maps, complex polynomial maps from Cn plus 1 to Cn, regardless of the dimension, if you have a constancy of the Euler characteristic, and if you don't have vanishing at infinity with that definition, and of course you were looking here only at regular values, then we have local triviality. Yeah, so it's the same theorem as in the real case, but now for map from Cn plus 1 to Cn. This can be seen as a generalization of the Suzuki-Halle theorem, but in higher dimension. And I should say that the first theorem that I mentioned is in fact a corollary of this theorem. Sorry. I mean, if you look carefully. And the other consequence is this one, because you saw that the 2 example dimension, in one of them, you had some C stars and copies of C stars, and the other one was just lines C. And you saw that maybe you can think that, look, these are kind of simple examples. But it turns out that if you have fibers with more complicated topology, actually you're not going to have those examples. So this is the statement that if you have the constancy of the Euler characteristic, and if you know that the Betti numbers are large enough, then you have local triviality. So the first part is Euler characteristic constant, and the first Betti number is at least 2, then you're okay. And the other one, it says that if the Betty number of fish fiber is at least 1, but you have constancy of Betty 0 and Betty 1, then again, you're okay. So in some sense, those two examples are the worst, if you want, that you can get. The one with C star union C star and the one with C union C. Yeah. So curves. So here, so everything here is about maps. Cn plus 1 to Cn. And not only that, but if you look for maps from C4 to C2, so with two-dimensional fibers, then it's not going to work anything. I mean, it doesn't work. The statement is not true. Sorry. Now, I will say a few words about the proof. The first thing that I want to mention is it's a nice result of, maybe it's going to be useful for you in general, I mean, in some other context. It's a result of Palmeira. It's a paper in Annals in 78, and then extended by Gael Menez, in a paper in Transactions in 2002. That says that if you have a smooth submersion, and if the fibers are diffeol to some r to the power p, then the map is locally trivial fibration. So once that you know the fibers are nice, I mean the RP, then you're okay. And Palmeira did it for maps with target one-dimensional, and Menez did it in general. Yeah. So that means that if you know that our map here has as fibers C or C, then you're in good shape. What if not? If you have a Riemann surface and it's not simply connected, but you like to do something with simply connected Riemann surfaces, the first thing that comes to mind is to look at the universal cover, right? And for that, I'm going to assume that the fibers are connected. So let's say that you are in this situation. You have a polynomial map from Cn plus 1 to Cn with connected fibers, but not necessarily simply connected. And take the universal cover. But when you take the universal cover of a fiber, I mean, you can do it fiber with fiber, right? You have them, but you have them separately. Now you have your map. You have to do it jointly. So what you try to do is to do some kind of uniformization in families. You have a family of Riemann surfaces, whatever that means. You want to take the universal cover of each member of the family, but you have to put them together. You want to put them in the same bunch, right? And the question if this is possible. Well, it turns out that, of course, this kind of question, which is natural and old-fashioned, at some point people thought about it, yeah, during the history of mathematics. We have him, mathematics has more than 2,000 years in history, right? Riemann surfaces don't, but and the answer, as I said, is yes. And Ilyashenko did it. There are two papers that deal with this kind of stuff. We have them here. And what Ilyashenko proved? He talked about foliations. I'm not going to give his statement in full generality, but for our purposes, it's enough to work in this context. So you have a holomorphic submersion between M and B, and you know that the fibers have dimension 1. Moreover, you assume that M is Stein. For now, I'm not going to define Stein, I'm going to do it in a second, but it's just some property that M has. Then you can find the complex manifold M tilde, that sits above M. So we have B here, M, and here M tilde, such that when you look at this map here, M tilde to M, this is nothing else than the universal covering of every fiber. So here you have a point. Here you have the fiber, let's say MX. And here you take the universal cover of M. And this manifold M tilde comes with a projection map pi, which is a locally bioholomorphic map. That tells you that if you look from M tilde to B, this is submersion, and the fibers of this map here are diffeomorphic to R2, either disks or complex line, depending on your look. I wrote the diagram, so in our case, this was U was B, F inverse of U was M, and the tilde F inverse of U was M tilde. So because here you have some merger with fibers diffeomorphic to R2, this is locally trivial. Why? Because we have that result of Palmeira-Méniez. But doesn't mean, so if this is trivial, you don't know that this is trivial, right? I mean, why should it be? So you don't know yet that F is locally trivial. However, this is a proposition proved by Gael-Méniez in the same paper that I mentioned, transaction paper, which is again specific, and it's important here that you have the right dimensions. So you have a diagram like that over there. It's the same picture that you have it on the board, but we've done it like that. If it happens that this is a smooth submersion, which is our case, we work with the regular values. This one is locally trivial, which you know right now using Palmeira-Méniez. And if pi here is a covering map, then P is locally trivial. So if you look at this picture, what you need now, the only thing that you need is to show that this pi here is a covering map. Ilyashenko theorem gives you only locally bioholomorphism. Locally bioholomorphism doesn't mean now necessarily covering, right? So I hope that you're aware of that. And in general, it's not true that this map given in the map given by Ilyashenko is not true that it is a covering map. So you have to prove it in our case, you have to prove it, because in general it's not true. So it's the same that I said. So we don't know that. We don't know that it's a covering because Ilyashenko guarantees only locally bioholomorphism. And now, how do you prove that this is a covering map? First of all, you look at that proof that Yashchenko gives. Yeah. And then when you do that, you realize that what you need, you have to control the way that the fundamental group of the fibers moves in fibers. So you have the fundamental group of each fiber, but you move the fibers, and you want to understand exactly, you need some kind of continuity of the fundamental group if you want. And it turns out that some facts about Stein manifold are useful now. I mentioned the word Stein before when I wrote the Ilyashenko's result. And I don't think that it hurts you to know what a Stein manifold is, even if you don't know yet. But I think it would be useful for you in general. The easiest way to give the easiest way to define it is like that. So a complex manifold is called Stein if and only if can be embedded as a closed-sum manifold in some affine space. This is not the original definition, and it's not the best one, but this is the easiest to state. Another way to say that is that a manifold is called Stein if it has enough holomorphic functions, global holomorphic functions. Think about when you proved Wien embedding theorem. I don't know when you but maybe you remember that you actually didn't prove that you have one embedding. You proved that you had many embeddings, right? It's a bare category argument. Yeah. The same story here. In fact, you need many holomorphic functions to embed the Stein manifold in Cn. And there is one way you can define it in a better way. But it turns out that this definition, or any definition, is equivalent to the theorem over here. In fact, this is the theorem slash definition. A complex manifold is Stein if you can find on this manifold, it's a complex manifold, a C2 function, a function with values in R, such that it goes to infinity at infinity. This is the meaning of the fact that the level sets phi less than C. Each level set is compact. Yeah. So when you go out, you look at this level sets, they're all bounded. And moreover, this matrix, which is a kind of complex Hermitian, is a complex Hessian. Sorry, so the complex Hessian, but written in complex coordinates, is positive definite. A function that has this matrix positive definite is called strictly Puris harmonic. And here you see some coordinates. This is a manifold. These are local coordinates. But the notion that the fact that this matrix is positive definite does not depend on the choice of coordinates. So it makes sense. You can put this definition on manifolds. And for you, this should be more exciting, because with this kind of functions, you can do more theory. Yeah. So you should be happy to have this kind of functions. And I wrote here some examples. Convex sets in Cn, real convexity, here, are Stein. Open Riemann surfaces are Stein. A closed sum manifold of a Stein manifold is Stein. But a compact manifold is not Stein. By the way, compact manifolds, do they have many holomorphic functions globally defined? Yeah, so I hope it's clear. On a compact manifold, complex manifold, you don't have non-constant global holomorphic functions. Yeah, global holomorphic functions have maximal principal even if you're talking about manifolds. Yeah, so that's the reason why. Okay, and so if K is a compact set in Siena, in my tech I didn't put the backslash, and yeah, then the complement of a compact set in Siena is not Stein. Yeah. So you have here some examples. I mean, just to And here, one more definition. And I don't know what course you took in one complex variable, but maybe you had in that course the Runge theorem. Does it ring a bell? Yeah. So it is about approximation of functions with globally defined functions on some open set. This is called Runge. And this is the same story here on any Stein manifold. So you have an open set omega in M, and M is called omega is called Runge if it's Stein, and if every holomorphic function on omega can be approximated by holomorphic functions that are defined on the entire M, and the approximation, the topology that you work here in complex analysis, the natural topology is the topology of uniform convergence on compact sets, compact open topology. Yeah, so this is the definition, and if you look back at your one complex variable course, you'll see something like that. And if you talk in general about Riemann surface, not only about domains in C, this is the content of the Runge theorem in one dimension. So you have an open Riemann surface, and so I said open Riemann surfaces are all Stein, so that's not an issue. And an open set is Runge if and only if this morphism at the level of H1 from D to S, this is induced by the inclusion. If this is one is injective. Yeah. And one example, if you have a Stein manifold M, you know that it has has pluribus harmonic functions, and a level set like that is Stein and Runge. So we have examples of Runge open sets in Stein manifold are given by something like that. Yeah. And it turns out that what you can prove is this theorem that in general, if you have a holomorphic map between complex manifolds, and if you assume that M is Stein, and you assume that the Betti numbers of each fiber are finite, the fibers are connected, then lambda naught is not a bifurcation point if and only if the Euler characteristic of the fibers is constant. But this is for connected fibers. Of course, if you have connected fibers, you don't have vanishing. There is nothing to vanish. But this is an important step in proving in fact, it's one of the main steps in proving the theorem. If you have connected fibers and you have constant Euler characteristic, then you have the constancy of the Euler characteristic gives you local vanishing. And again, to prove this one, it was the same scheme. You use Steines together. From the Steines, you use these exhaustion functions with the pluribus harmonic functions. You have the level sets that are Runge, and the intersection of each fiber. So you have phi less than C. This is Runge in M. And when we intersect this one with some fiber, this is going to be Runge in F inverse of T. This is a Riemann surface. The Runge property means exactly injectivity at level of H1. And this is the result that you use, because this one moves continuously if you want. So this is the continuity of pi 1 that you need to show everything. And this is for connected fibers. And what happens if the fibers are not connected? you have to work connected component with connected component and to put them together. So you have here a connected component. You make here a small box, and once that you make the small box, you show that each fiber intersects this box only in a connected component. So that means you don't have two connected components of the fiber that are passing to this small box. And then you make them in a bunch, and you show that what you get here is something open and Stein. But that's the story. Yeah, and one word of advice. So here we have this Stein stuff. Maybe you say we didn't need Steiners. Maybe there was another way to do something like that. But if you go to maps without connected fibers, you're going to have some open sets in CN, but not the whole CN. Bunch of open sets in CN. They're not going to be algebraic. Even if you like an algebraic world, if once that you have several connected components, you get out of this algebraic world. That's the life. Yeah, so you don't stay in the algebraic world. Okay, so I'll stop here. Mm-hmm. Okay.